Welcome to Chapter 8 of our course on Communication Acoustics. My name is Stefan Weinzierl. I am head of the Audio Communication Group at TU Berlin and will introduce you to the principles of binaural technology as one approach to the generation of virtual acoustic realities. In the first part of this lecture, we will have a look at the concept and the implementation of static binaural synthesis. In the second part, we will look at dynamic binaural synthesis, some requirements for a convincing implementation, and at the quality of the virtual environment which can be attained with such an implementation. One thing before we start, I would ask you to listen to the lecture with headphones, because some of the demonstrations will only work with headphones, and so does binaural technology in general. So if you don't wear headphones, please stop the video for a moment, get you some headphones and make sure that the right-left orientation is correct. Now let's start with a picture. It is from Albert Bregman's famous book on auditory scene analysis, and not only illustrates how we perceive our environment acoustically, it can also be used to explain how binaural technology works. You see a lake with a certain size and shape and some boats moving on this lake. And you see a person who has dug two canals connected to the lake and put two tissues on the surface of these canals. The tissues will move up and down a little whenever waves coming from the lake will hit the two canals. The task is now to only watch how these tissues move and conclude from this movement how many boats are on this lake, where they are and how fast they move, and what the size and the shape of the lake is. If you think that this is impossible, I have to tell you that this is exactly what you do every day if you listen. All you have are the two eardrums, which are two membranes moving back and forth in one direction, just like the tissues on the picture, and your higher auditory processing stages, which are able to extract all the information from this movement. This shows how powerful our auditory system works with only very little sensory input, but it also shows how we can generate the same auditory impression in virtual reality. If we were able to move the two tissues in exactly the same way as they move in reality, we can expect that our auditory system will see or hear the same acoustic environment as a virtual sound image. And that's what we do with binaural technology. The boats are the sound sources. For example, a loudspeaker in a room, like here on stage. The waves are traveling as acoustic waves through the room, and they finally excite the two membranes in our ears, from where our auditory system gets all information. In order to move these membranes in the right way, we need three things. We have to know how the sound source excites the room at the place where it is. We have to know how a certain excitation at the source position will translate to a movement of our eardrum at the receiver point. And we need a rendering algorithm and a reproduction system that generates this movement. From the perspective of signal theory, this is a classical transfer system problem where we have a source signal, an impulse response describing the transfer path, and an output signal generated as a convolution of source signal and impulse response. We can write this in the time domain as a convolution or in the frequency domain as a complex multiplication of the corresponding Fourier transforms. Remember Chapter 2 of the lecture series, where Jens Ahrens has explained this in more detail. For a system for binaural synthesis, the important part are these transfer functions, describing the sound propagation from a point in space to the human eardrum. If these transfer functions are measured in an anechoic environment, they just describe the properties of the human ear as a receiver, and we call them head-related impulse response in the time domain or head-related transfer function, or HRTF, in the frequency domain. It's always one for the right ear and one for the left ear. If they are measured in a reverberant environment, they describe the properties of the ear and the surrounding space, and we call them binaural room impulse response or binaural room transfer function. HRTFs were introduced in Chapter 3 on the anatomy of the hearing system. They are characteristic for a certain angle of sound incidence, for example, at 90 degrees to the left and 0 elevation, and from the two impulse responses and their corresponding Fourier transforms, the HRTFs, we can extract certain features. Let's have a look at the impulse response and the corresponding HRTF. And from these, we can extract certain features such as the interaural time difference or the frequency-dependent interaural level difference, which we assume are important for our sense of localization. The ability of the auditory system to decode binaural signals can be nicely demonstrated if we listen to binaural signals where the transfer function is introduced automatically by using an appropriate recording system. Hello again. We are now in the Anechoic chamber of the TU Berlin, a room which is very important in acoustics because here you can study the behavior of sound sources or other acoustical phenomena without the influence of sound reflections from the walls. These are completely absorbed by the thick wedges of porous material. What I would like to demonstrate is the properties of binaural signals, which means signals that went through the binaural transfer path from a certain angle of incidence to the human eardrum and thus have all the spatial characteristics of the source encoded in their signal. Make sure that you listen with headphones because otherwise the effect will not be audible. At the moment you hear me as a mono signal recorded with this clip microphone at my chest. If you close your eyes, the sound should not give you any clue about where it comes from. And if I move in space, nothing changes for you acoustically. Signals without binaural characteristics tend to get located within your head, somewhere between the two ears. What we have here is a so-called dummy head. It is modeled after the human head, including the two pinnae in particular, and it has two microphones located some millimeters inside the ear canal. If we now switch the microphone from the clip microphone to the two microphones of the dummy head, several things should sound differently. First, you should be able to localize me outside of your head at a certain position in space. And if I now move, you should be able to follow this movement and notice, for example, that I am now at your right, that I am now at your rear, that I am now approaching the left side and now come back to the front again. I would recommend you to listen to this section again and close your eyes, because the visual input will always try to dominate your sense of localization. If we switch back to the clip microphone, this effect disappears and you will have again an internalized sound impression. So let's conclude that the properties of the binaural transfer path, with its interaural time and level differences, as well as the corresponding spectral cues, are responsible for our ability to localize sounds in space. These characteristics can either be encoded in the signal itself if you use an appropriate microphone like this, or they can be synthesized by measuring the binaural transfer function separately and later convolve the binaural impulse response with any source signal. If we compare head-related impulse responses and binaural room impulse responses, we see that an HRIR is a quite short impulse response, only about 2 to 3 milliseconds long, whereas a BRIR is as long as the reverberation of the room it has been recorded in. We can see this better if we don't plot the linear amplitude, but the squared amplitude as a level, so logarithmically. Now you see the power of the signal over time, and you see some strong early reflections, for example the floor reflection or other early reflections that might come from the ceiling, from the side walls. And you see a dense pattern of higher order reflections towards the later part of the impulse response. Now, if we want to generate binaural signals, not by recording with a dummy head, but by convolution with the corresponding impulse response, we have a system like this. The binaural room impulse response is convolved with a source signal and applied directly to the eardrums with headphones. The source signal should not contain spatial information itself, because we would then have two different and inconsistent spatial signatures, so it should be recorded in the anechoic chamber. The binaural impulse responses can be recorded in real environments with some kind of binaural receiver and with sweep signs, for example, as was explained in Chapter 2. They can also be produced with a software that simulates the sound propagation in space. These algorithms are introduced by Michael Vorländer in Chapter 11 on room acoustical simulation. They generate a pattern of sound reflections arriving at a certain receiver point in a reverberant space. And to make a binaural room impulse response out of this pattern, each individual reflection has to be convolved with the HRTF corresponding to its angle of incidence, a processing step which is not necessary if you are only interested in normal room impulse responses. So we could call this a model-based and a data-based version of binaural synthesis. In the second part of the lecture, we will extend this picture with an interaction for the listener's head movement. But for the moment, we will consider only the static case and have a closer look on how to measure binaural impulse responses and how to playback them. For the recording, you can either use one of the binaural microphones that you would also for direct recordings, such as the Neumann head, which you saw in the video before at the left. Some of them are an imitation of the human head only and are called dummy heads. Others include an imitation of the head and the upper part of the body, such as the two at the right, which are called head and torso simulators. Since the HRTF is a result of everything that happens to a sound wave before it arrives at the eardrum, you can imagine that also sound reflections at the shoulders can have a notable effect on the binaural signals. With its robotic neck joint, the system at the right is prepared to produce dynamic binaural simulations, which we will address in the second part of the lecture. You can also use your own body and head as a head and torso simulator by inserting a small microphone encapsulated in a silicone or foam plug into your own ears. In both cases, the question is, where exactly and how should the microphone be positioned in the ear canal? Remember that the ear canal from its entrance to the eardrum is about 30 millimeters long. Since for binaural synthesis we want to excite the eardrum, you could think that intuitively it is better to record as closely as possible to the eardrum. This is, however, not necessary. The most important point is to find a position where all directional information about the angle of sound incidence is already encoded. If the rest of the transfer path from this point to the eardrum is then a linear system, independent of the angle of sound incidence, we can account for it either with an equalization filter or by compensating the reproduction at the same reference point, so that the rest of the transfer path will be identical both at recording and reproduction. On the right picture, you see measured transfer functions from different positions in the ear canal to the eardrum. with sound sources at 3 different angles of incidence: in front, from the side, and from behind. The transfer function from 12 millimeters inside the ear canal to the eardrum is, except for small measurement uncertainties, identical for the 3 angles of sound incidence. The same applies to a position 6 millimeter inside the ear canal. At the entrance of the ear canal, differences start to appear above 5 kHz, which get bigger the more you leave the ear canal. So we can keep as a result that a position at the entrance or some millimeters inside the ear canal will be appropriate for the measurement of binaural impulse responses. The second question is, how should the microphone be applied there? In the open ear canal or in the blocked ear canal? Well, it can be shown that with a probe microphone in the open ear canal, it is not only tricky to keep a defined position of the microphone, but the microphone would also collect unwanted sound reflections from the eardrum back into the ear canal. So the standard approach is to place a small microphone some millimeters inside the blocked ear canal. And this is what you have on the left picture, with a silicone plug holding the microphone and blocking the ear canal at the same time. This is then the reference point to which your reproduction system should be equalized. And that's where we have the next challenge. If we want to recreate the sound pressure in the ear canal by live recording or by convolution, both the recording microphones and the headphones should be acoustically transparent, which means they should not introduce any spectral differences into the transfer path. Headphones, however, are far from having linear frequency responses. If you measure headphone transfer functions on a dummy head with a microphone in the blocked ear canal, you can see that even high-quality devices, such as those on the picture, tend to have a low-frequency cutoff around 100 Hz and sharp peaks and dips above 5 to 4 kHz. These could theoretically be linearized with a powerful inverse digital filter, but then another problem arises. In the picture you see, for each headphone, measurements with repositioning, so after removing the headphone and putting it on again. And as you can see, already a small difference in the position of the headphone on the head will lead to significant differences in the frequency response. These are particularly large for closed headphones, like the one left on top, and not so large for open headphones, like the one left bottom, or for so-called extraoral headphones, like this one, which don't act against a closed air volume around the ear. These differences are even more pronounced if you measure them on different heads. So a perfect compensation for my head would not be perfect for another person's head. And if we would try to compensate now these sharp dips with an equally sharp peak in the inverse filter, and if this dip will be slightly shifted in frequency due to repositioning, the inverse filter might even make it worse due to the resulting mismatch. That's why compensation filters are usually designed to linearize the high-frequency response only to a limited extent, a feature called regularization in signal processing. Nevertheless, a system for binaural synthesis needs an equalization filter that compensates the unwanted frequency response of the recording microphones and of the headphones for playback. Remaining frequency response nonlinearities can affect both the timbre of the original signal as well as the spectral cues of the binaural impulse response, and thus lead to a reduced accuracy of localization. If we now summarize the first part of this lecture, we can recapitulate that binaural synthesis aims at creating virtual acoustic environments by reconstructing the sound pressure in the human ear canal and by exciting the human eardrum in the same manner as it would be in reality. This is reached by convolving anechoic source signals with binaural room impulse responses and by playing back the resulting signal with headphones. We can, by the way, consider head-related impulse responses as a special form of binaural impulse responses, which convey only the location of the source but no impression of the spatial environment. Binaural room impulse responses can be measured with dummy heads or head and torso simulators in real environments, or simulated by room acoustical simulation based on 3D models of the virtual environment and by applying HRTFs to each individual sound reflection. So, binaural synthesis needs a careful control of all processing steps, and inaccuracies may result from, for example, the non-individuality of BRIRs measured with dummy heads. So using the BRIR of a dummy head is like listening through another person's ears, unless you use your own ears for the recording, which was mentioned as an option too. And inaccuracies might arise from the non-perfect compensation of the headphone transfer function, resulting in distortions of the timbre of the original signal and the spectral cues of the BRIR, and leading to a reduced accuracy of localization. A principal limitation arises from the fact that with the system as we have considered it so far, there is no interaction between the listener's head movement and the simulated environment. So unlike in real environments, where an acoustical scene remains stable no matter how I move within that scene, the simulations we have discussed so far will move with me when I move my head with the headphone on. There is an approach to overcome this limitation, and we will discuss it in the second part of this lecture. But even without this extension, and even without your headphones at home carefully linearized, it is an impressive thing if I just use a pair of binaural room impulse responses in order to relocate my voice to different spaces. Such as the Comical Opera in Berlin, for example, where you now sit in the 9th row and listen to my voice on stage. Or to the Gewandhaus in Leipzig, the home of the famous Gewandhaus Orchestra, where I already have to try hard to make myself audible. Or to Eberbach Abbey, a monastery with its large Romanesque church, built in the 12th century, with a reverberation time of about 5 seconds in the mid-frequency range. Back in the studio, I'd just like to show you the references that I used and hope to see you again for the second part of the lecture.